Alright guys, this is the last section of 4.1. We're going to talk about the Bohr model and Lewis dot diagrams, which means we're now going to focus in on the electrons within the atom. There's a famous scientist named Niels Bohr. He's actually a physicist, and he performed experiments with hydrogen and light. And he is the scientist that actually came up with the atomic planetary model. You can see that the nucleus is in the middle, just like Rutherford had mentioned earlier on, full of protons and neutrons. And at the time that Rutherford put the model together, he thought that the electrons were just scattered about in the electron cloud. And Niels Bohr is going to be responsible for determining that the electrons are actually found in energy levels and they travel a pathway. So Bohr believed that electrons were located in energy levels, and sometimes that is referred to as a shell. And one of the things that you need to know is that certain energy levels have a certain amount of energy associated with them, and in order for electrons to be held within that energy level, they have to have that same energy. Let's think of the energy levels within the electron cloud as rungs of a ladder. The nucleus is down at the bottom, and the rungs of the ladder are labeled as first, second, third, fourth, fifth. Think of those as the energy levels. And you can see that if an electron is in energy level 1, it's closer to the nucleus. If an electron was up in energy level 5, it would be farther away from the nucleus. The higher the energy level, the greater the amount of energy associated with those electrons. And what we've determined is that electrons like to have the lowest energy level, want to be in the lowest energy level possible. They want to have the lowest energy state, which we call the ground state. When electrons are in their ground state, they are going to be as close to the nucleus as feasibly possible. And when they get extra energy to them, they will be able to jump up to higher energy levels. When they are in those higher energy levels, we call that an excited state, and the amount of energy that's going to get them to that higher energy level state is called a quanta. So a Bohr model is just a simple structure that shows us where the electrons are within the energy levels. There is a YouTube clip that you can click on if you would like to see a little bit of more information. But basically what it comes down to is that only certain numbers of electrons are allowed within certain energy levels. In the first energy level, or the first shell, only 2 electrons can reside. After that, electrons need to be put into the second energy level, where only a maximum of 8 can be placed. In the third energy level, there's a maximum of 18, and in the fourth, there's a maximum of 32. When we are in the third energy level, though, not all 18 electrons are in the energy level all at once. And so it's going to be important for you to understand that only 8 electrons can be placed in the third shell at first, and then 2 electrons will move into the fourth shell. Any remaining electrons will be placed back in the third shell until the maximum of 18 are in place. What I just said might sound a little confusing. I'm going to go through a couple of examples in a few minutes that will show you how to do that. And I'm just asking at this point that you just know this, and to let you know that it will be explained in the next section. Once we talk about the dynamics of each energy level, what I just talked about will make sense. The last thing we want to talk about is that the valence electrons, these are the electrons in the highest, most outermost energy level, are really the ones that we want to focus on as we move into the next couple of sections. So I just want you to be aware of the valence electrons. There's inner core electrons, which are the electrons closest to the nucleus. And then there's the outer energy shell electrons, which are called the valence electrons. And those are the ones that we're going to target and then use as we move into the next few sections. Okay, so let's try a couple of examples. We're going to start off by drawing the simplistic model of hydrogen. We know hydrogen has 1 proton, and so I'm going to go ahead and I'm going to draw a nucleus, and I'm just going to put 1 p in it, and then I'm going to go ahead and draw an energy level. We know since there's 1 proton, there's 1 electron, and I'm just going to go ahead and just put 1 little dot on the outside. You could also just actually write 1e as well, and that would be your simple Bohr model. We're going to go ahead and take a look at the next one, which would be helium. We're going to draw on our nucleus. This is atomic number 2, so we know it has 2 protons. And we'll go ahead and draw in an energy level as well. We know with 2 protons, there's 2 electrons. And I'm going to go ahead and just drop in that 2. That is the maximum number that can fit in the Bohr model. We're going to move on to lithium. Lithium has a nucleus again. This is element number 3, which means it has 3 protons and 3 electrons. Now remember, in the last example, we had 2 electrons in the first energy level. That was the maximum that we could put in there. And so now we do need a second energy level. We know that 8 can reside in the second energy level, but we only need to place 3 electrons. So we're just going to go ahead and put the third electron in the second energy level. We're going to move on, and this time we're going to look at sodium. So sodium has 11 protons, which means it's going to have 11 electrons as well. So I will need 3 energy levels this time. And the reason for that is we're going to put 2 in the first. That's the maximum that can reside. 8 in the second, so that gives me 10. I have 1 more, and I've reached the maximum capacity in the second energy level, so I have to put that third electron in the third energy level. Last but not least, we have iron. Iron has 26 protons, and so I'm going to need 26 electrons. So let me go ahead and draw some energy levels here, and we'll get started. So we know that there's a maximum of 2 electrons in the first, 8 in the second. So this is where we need to be thinking about the special situation that happens in the third energy level. We said that we can put in 8 at first, and then we're going to go ahead and drop in 2. So if I add that up, I've got a total of 20. I need to add 26. So that means that I'm going to add another 6 electrons back into the third energy level. Remember, the maximum that I can have is 18, and right now I have a total of 14. So everything's good, and we are now finished. You can see that there's a total of 26 electrons, 2 in the first, 8 in the second, 14 in the third, and 2 in the fourth. Let's talk about one more thing here, our valence electrons. Remember, our valence electrons are our outermost electrons. Since in the hydrogen atom, we only have 1 electron, that is also going to be the 1 valence electron in hydrogen. And the outermost electron of helium is 2, so that's how many valence electrons it would have. When we got to lithium, you can see that now the outermost electrons are in energy level 2, so there would only be 1 valence electron in lithium. In sodium, there is once again only 1 valence electron, so we're looking at the highest energy level. And in iron, we would have 2 valence electrons. Valence electrons are the electrons in the highest energy level. Everything else is considered an inner core electron. Another way to show electrons within the atom is a Lewis dot diagram. This one is just going to focus in on the valence electrons of the atom. We will use a symbol of the element to represent the nucleus and the inner core electrons, and we will use dots to represent the valence electrons. Only 2 dots per side. There can only be 4 sides, a north-south and east-west position around the symbol, and only a maximum of 8 valence electrons will ever be found in these diagrams. There are some rules. As we add the electrons, we're going to put 1 dot at a time on each side until each side is half full. Then we add a second dot to make a pair when needed. The exception is going to be helium. Usually when we do helium, since it has 2 valence electrons, we would go ahead and we would put 1 dot on one side and another dot on another. That would be our Lewis dot. However, since helium has 2 valence electrons and it is a noble gas, we are allowed to write it like you see in the box. No other element with 2 valence electrons would be able to be written this way. This would be the most appropriate way right here. Here's a quick view of a bunch of elements that have their Lewis dot diagrams drawn for you. And one of the things that you will notice is that there's a pattern. And once again, the pattern is we put 1 electron on each side before we go back to make a pair. You can see that as we move from lithium, beryllium, boron, and carbon. And then we add the additional electrons around, and and you can never have more than 8 valence electrons. And you can see that each group on the periodic table also is going to have the same number of valence electrons. And you can see this one has 8, this one has 7, this one has 6, and so forth. And I just want to point out to you that if we go back to the periodic table and we look at the group numbers next to the letter A, we will find out that the valence number of electrons actually correlates to that number. And so you can see here that in group 7A, those atoms will have 7 valence electrons. In group 4A, those will have 4 valence electrons, and so forth. The only time that doesn't work out is for helium. Helium, even though it's in group 8, only has 2 valence electrons. It was shortly determined that the Bohr model was not accurate, and in 1920 the quantum mechanical model came into existence. Modern atomic theory using calculus was able to show that the electrons acted as both particles and waves. And because of these properties, the electron in the atom's position became different than what we used to think. There are still a lot of correct ideas that the Bohr model gave us, and so we still use it to simplify the atom. But as we move into the next section, we will actually talk about how electrons can be found in a region of space called an orbital. And an orbital is just a location within the atom where there's a high probability of finding the electron. This model gives no information about when the electron occupies a certain point in space or how it moves, but we have pretty good reason to believe that we will never know the details of electron motion no matter how sophisticated our models may become. We do feel confident, however, that the electrons do not orbit the nucleus as suggested by the Bohr model. The picture to the left is a probability map of an atomic orbital. You can see that there are many dots around the nucleus. Those dots are electrons. If we were to take a snapshot of the electron every time it moved its position and then created this three-dimensional map, you could see that there is a high probability of the electron within a certain region. And so that is the atomic orbital, and that would actually be the s orbital of the atom. If we look to the right, you will see that there's lots of different orbitals within this diagram. We have s orbitals, p orbitals, and not seen in the diagram, d and f orbitals. They have different shapes, and they are located within different energy levels as well. As we move into electron configuration, we'll talk more about these orbitals. This concludes our first section dealing with the atom. I'll see you around.